Hi, everybody. My name is Mian Xiao. Today, I would like to present my work, Domain Partitioning Material Point Method for Evolving Multi-Body Thermomechanical Contacts during Dynamic Fracture and Fragmentation. Uh, this work is submitted for the special symposium in honor of Professor Frank DiMaggio, who is a genius in constitutive modeling and introduced the CAP+ system model. So in this work, we also have something related to the material inelastic response under large deformation, which is quite related to Professor DiMaggio's work. Let's start on the motivation. We are particularly interested in the particulate system, which is very helpful for understanding granular materials. But such system could be difficult to model. As we can see in this particle crashing experiments, we need to consider multi-body contact interactions, and we may have evolving crack. And while fragmentation, those materials can undergo very large deformation, and the entire experiment may be rate dependent, and we need to consider a thermal response under high loading rate. So we propose a material point method framework with domain partitioning to capture all of these complicated thermomechanical behaviors. Next, I would like to introduce the theoretical formulation. This is our problem domain, and with the Dirichlet mechanical and thermal boundary conditions, gamma U, gamma theta, and normal boundary conditions, gamma Q and gamma T. In the domain omega, we have two governing equations to solve. One is the balance of linear momentum. The other one is the balance of energy, written in terms of temperature rate. And on the contact boundary condition, gamma C, we need to consider the mechanical contact response, which is stated as these two KKT conditions. One is for the normal, response, basically the normal non-interpenetration condition, and the other one is the tangential response following the Coulomb's friction law, which states that the tangential contact pressure PCT cannot surpass some critical friction, which is equal to frictional coefficient mu c times the normal contact pressure PCN. The last equation is the thermal contact response as the balance of energy on the surface. This is stated as follows. So the contact heat flux QC has two contributions. One is the cross-interface conduction, written as some contact conductance coefficient Hc times the temperature jump, middle bracket of theta. The other one is exactly the contribution from frictional heating. This slide presents the constitutive assumptions we use for this framework. We assume the continuum body to be elastoblastic material, where the damage field is important for characterizing the failure, which functions as a continuum damage approach for dynamic fracture modeling. The hyperelastic material response is assumed to be compressible new hooking, and the inelastic damage behavior is governed by the Rankin's rotating crack model with mesh regularization. This is a non-local damage model. We refer you to this paper if you are interested in more details. The domain heat conduction law is simply the linear isotropic Fourier's law. Since the contact response is very important in our framework, I would like to emphasize the thermal contact constitutive laws. One is for the contact conductance Hc. This is dependent on the normal contact pressure Pc related by these constant gamma bar. The other one is for the frictional coefficient mu c. We assume that it can vary according to the temperature, maximum temperature on the contact surface. And we can see here, as we increase this temperature theta 1 maximum or theta 1, theta 2, approaching theta dam, which is critical temperature, this mu c is actually decreasing. And once we reach that theta dam, we won't have any friction on the contact surface. The domain partitioning approach in this framework is of great importance because we need this to identify if there's a contact or potential fracture separation. The technique we use is called damage field gradient partitioning, proposed by Homo and Herbert. Here we construct the smooth damage field and obtain this non-local gradient at those black arrows. And the body partitioning only happens near the cracked surface, which is represented by these dark, fully damaged stones. And at those interfaces, the damage gradients from two distinct bodies, as these two pictures shows, they are pointing relatively toward each other. And once we detect such damage gradients pointing toward each other around the green node, we're going to trigger the body partition. Next, I would like to talk about the numerical results. The first example concerns the thermal contact verification. We have two square elastic bodies, no gravity, so we need to apply the pressure P on the top in order that the two bodies contacting each other. The top boundary is hot, the bottom boundary is cool. So we have this type of steady state temperature distribution. This is a linear distribution with a temperature jump across the contact surface. The steady state temperature theta 1 and theta 2 is actually a function of P. So we have this analytical relationship. Because here HC is also a function of the normal contact pressure, so theta 1 and theta 2 is a function of P. We plot the analytical solution as a solid line, and those diamonds are actually the numerical results of theta 1 and theta 2 with different applied contact pressure P. We observed that the numerical simulation and the analytical results are pretty close, and this verifies the correctness of our thermal contact model. The second example illustrates the effects of thermomechanical coupling during multi-body contact. We have this type of geometry, and we apply a pressure in order to move everything toward the right. We assume frictional contact and simulate everything under three conditions. One is isothermal condition, the other is thermocouple condition. The last one is thermocouple condition with thermal softening on the friction, and this is the temperature constant we choose. So here we can see for the isothermal and thermocouple conditions, this disk cannot really go on to this step because it cannot overcome the friction here. But in the thermocouple condition, we actually have a large temperature accumulation near this contact surface. It could be around 900 degrees. This is because we have intensive compressive deformation and frictional heating here. So it makes sense to consider thermal softening on the friction. And here we can see that the results is greatly different if we consider thermal softening on the friction, because the disk can go onto this, pass this corner and go onto this step. The last numerical example replicates a lateral confined 3-particle crushing experiment conducted by Sylvia and Ashley. We assume the materials for the particles is fracturable. And we load from the top with different loading rates. One is 8 meters per second, Another one is 16 meters per second. The last one is 80 meters per second. We plot the temperature as the main result, and it is a good indicator of wave propagation. Also, it indicates the fracture pattern or crack pattern, because the concentrate of temperature increase is the locations where we have intensive post-fracture contact. So it mainly concentrate around those cracks. And the crack pattern indicated here shows that as we increase the loading rate, the crack pattern is becoming much more complicated, particularly for the top grain, which is completely fragmented. The reason is that when we increase the loading rate, the crack branching is much more intensive, and this leads to more complicated and more fragmented crack pattern. For conclusion, we propose a material point framework designed to replicate the fracture and contact mechanics under non-isothermal conditions. We incorporate DFG method for domain partitioning and thermosensitive contact for modeling thermal contact, and we have non-local damage models to capture fracture propagation. The proposed model here is capable of capturing the complex fracture patterns and the resultant contacts under different strain risks. And that's all for today's presentation. And we acknowledge our sponsors here. Thank you for your patience. Bye-bye.